Let's get started. I think I'm ready. So I've been doing a bit of preparations before jumping into doing this video. It's going to be a bit different than it's going to be something different, right? So it's not. I'm taking a step aside from the portfolio optimization now for one video to just do one session on this article from Brian, who basically there's been a bit of a back and forth between him and me. In Twitter about like a series of articles that he's been writing about, like building classifiers with like control swaps and basically sort of the swap test, right? Um, where to start, just to make sure that I can give you the best context possible. So what Brian is claiming is that well, first of all, so Brian is claiming different things here that I don't find really good. So he's claiming that he can uh, basically map like 100,000 K data points into like 4 qubits or something like these. Like and what he really I hope is it gonna let me? Come on, I don't want to have to pay for unlimited access. Um, but in reality, what it's doing, like if you let's just focus on this one, the last one, right? So because I think at the end of like we've been exchanging some tweets and whatnot, and basically what he just went ahead and did like a version of his algorithm, but for the MNIST data set, right? And so he keeps claiming the same thing. Was like he's encoding like hundreds of thousands of data points in just a bunch of qubits, and in reality, like if you go through these, and basically what he does is he takes the CSV data from like this, like the references. So this is really helpful, Brian, like that you actually put all the references in here. It's basically helped me to kind of try and reproduce the same. Uh, so because what I did is, and this is the preparation that I've done for these, is I took the same data set. I basically kind of worked on this. I did this off camera because it's just too big. I think Brian took the test data set. I took the train data set, which has more data. Um, but it just goes, it just was going really slowly. So it has data that looks like this, where you have labels and then you have each column is like a pixel, right? And so what Brian does, right, if you follow his algorithm in here, um, is so it's this 4 steps, right? So for each of the 10 classes, going from 0 through 9, calculate the normalized mean of each pixel by dividing the average value of each column by 255. So this is the first thing where it's like, this is just like a really kind of naive approach, okay? But what he's doing is he's doing what I did here, which is basically staking and I use this average if kind of function. So what I'm doing is, and I'm taking 50K rows. So for each pixel, it's averaging all those that like belong to the level 0, all the ones that belong to the level 1, and so on and so forth, and then dividing them by 255. So what you do at the end of the day get is you get like a long, so if you get like an average picture, like you can imagine without pain, right? So if you have kind of, 1 0, sorry, brushes. One zeros like this, another's like that, another's like that, another's like that, another's like that. So and you have like you have like maybe, I don't know, like 30K or whatever of these. So at the end you get like a kind of an average, like a picture was like that's your average 0, right? This is, and so first of all, this is like if you're calculating averages, right? Um, like if you take like 10,000 numbers and you calculate the average, you get a number, right? If you put that number into a qubit, then you're encoding one data point into 1 qubit. You're not encoding hundreds of thousands of data points into 1 qubit. You're calculating an average and you're encoding one data point into 1 qubit. So this kind of claim in here, it's already a bit misleading, but it's fine. So let's just go ahead and see, because what I want to do is I want to try to basically prove. I have the intuition that the way that Brian is doing it like does not like you don't need a QPU for these. Okay, I'm not saying I'm not saying the overlap test, or sorry, I'm not saying the swap test is not something quantum. I'm saying the way you're doing it, it's just you don't need a quantum computer for that. And yeah, so basically what he's doing is these, right? And that's what I did here. And then what he's doing is, the next step is for each of the 10 classes, sum the normalized means in a pattern inspired by a convolutional neural network. So he selected a 4x4 grid of 49 pixels. So 4 times 4 times 49, it gives you 784, which is the amount of pixels that the set has. So what he's doing is and then he goes ahead and he explains this here. I don't really understand. I think I don't understand much what the columns here mean. I guess they mean the columns of the data, but I don't know where the 49 pixels are in here. Because if I count, maybe the picture is just cropped or something. But here you've got like a 4x4, right? A 4x4 matrix or grid, and then in each grid you have to imagine there are 49 pixels, and so what he does is he averages these 49. So he says for the 16 squares for each class, sum and divide by 49. So basically what he does is, the equivalent of, if you have your, like let's say you've averaged your zero, so you kind of have something like that, and I'm really bad at drawing, right? So what he now does is he says, well, let's just take like, chunks like these, right? And kind of like so you basically reduce the dimensionality by averaging all the pixels in here and saying, okay, that's my one, like my square one, my square two, right? And so you kind of have your values in here, and what this would mean is you end up with a really blurred kind of zero, I would say. I don't know. So you've got the same blurry image, but like with less resolution, sort of saying. I think so. I think that's the right analogy. That's the way I understand it. Okay, so if what I did here is I basically what I did is I kind of did a trick with. I hope this is right, but it doesn't really matter at the end of the day. But I think it's correct. So I did basically I put in here the columns where the sums should start, and so this starts in column 2 because column 1 is column A, and so this starts at column B plus 49, right? So because B plus 48 is 49 pixels, and then the sums should start at column 51, and yeah, and so basically what this is doing is, what I'm telling it is I'm telling some, add like I'm calculating the range that I want to add things, right, based on this. I'm saying add the B to, and until B50, right? So that's what this is saying. So and then divide by 49. I'm doing exactly what he says, but I think the difference might be, I don't know if he handpicked those. It could be that he handpicked these here, but it shouldn't. I think my proof does not depend on these. I just wanted to show that because I know he's then going to complain that I didn't do this. So here it is. I mean, so you have, like I have here basically these 16. For the label 0, I have 16 numbers. For the label 1, I have 16 numbers. So I have like, all these kind of low resolution average, right? Um, and then and then at the end of the day, I just do a bit of cosmetic in here, so I can just take this string and copy paste it into my notebook. Yes, the same here. I'm going to make the same note as Brian said. You don't need to do this in Excel. You can do this in with Python NumPy. I just wanted to follow his process step by step. So, but what I did is I created a Brian MNIST notebook, and I just copied the data in here. And then I did sort of the same process for a value that I randomly selected. Randomly. I mean, what did I do? So what Brian does is he then tests these against 0, right? So where's the article? So he goes and he says, now we're gonna get a 0. Now we're gonna get a 0, and we're gonna test it against a 0, right? So a test number that is supposed to be a 0, and then he goes and he's like, those are the results. So it's a 92% chance is 0, 91% chance is 1, 84% chance is 2. Like, this shows you that, like, what you're getting is really an average result. Like, what you're getting is really like, um, you're comparing against an average. Like, the fact that those numbers are so equal actually should tell you that there's not so much confidence in these. But okay, he still claims that this is the selected value, which is 0. Fine. Um, cool. I think that's enough of background. That's enough of a background, because then what I did is I went here, I just picked like a row randomly. I picked 110 where there's a 0. So I picked this row and I kind of, flush it through the same process. So I created the test row in here. I created the compressed, like um, the low resolution version here, and sort of I kind of had it here. I added it here, and what I did is I copied the code that I shared with him like a couple weeks ago. I shared the code where I said, look, you can just calculate the Euclidean distance between these 2 points, like between these points. Like, if you imagine that these are points in like a 16-dimensional space, and you calculate the distances, that's kind of effectively doing the same, right? Like, the let's think about what the swap test is doing. So what the swap test is doing is just calculating uh, it's calculating how much overlap there is between 2 vectors or 2 states, right? And if you think about a state as a vector, and you can just think about 2-dimensional vectors, like if your vector A is just like these, and then your vector B is just like these, right? And let's assume they're all unitary because it's quantum computing and all that stuff. So it's just let's assume it's the same nodes. They're all like size 1 or length 1. So what this tells you is how much overlap kind of there is in here, right? And what the swap test will tell you is if they are like fully overlapped, then the probability of measuring 0 is, I think, 0% or something like that. Whereas if they are orthogonal, it's going to be 50%, something like this. If I'm not wrong. So I think I have. Did I? So swap test. By the way, I'm gonna close the Excel file because it's just gonna burn. I think I don't want this to burn too much CPU, but I think I saved it, so it's good if I just close this. So I just don't want to. I copied all the data in here, so we're good to go. And so test Wikipedia. That's probably enough of a background. And now we're going to start a bit improvising, okay? So I don't know if I'm going to be able to prove it. I kind of think so. I think my intuition is right. So what the swap test is doing is basically, as they say here, right? So if the 2 are orthogonal, then the probability that 0 is measured is 1/2. And if the states are equal, then the probability that 0 is measured is 1. So it's 100% 0. You have a quick quirk implementation that I was playing with earlier today. So you have 2 simple states, and they are equal, so this is 0, right? And I'm not going to get into why this is. It's got to do with sort of the different branches that this is creating. Yeah. So my point is that, like, my intuition. So what is my intuition? My intuition is that if the states you're comparing are known, like you know which states are they, and you know how to generate them, like you should be able to compare the sort of the generator of the state with each other, the generators of the 2 states, and kind of by measuring how different they are, like some sort of cost or some sort of distance, you should be able to kind of already know whether they are the same or not, because they basically, if you have the same parameters, and let's assume we're just, for the sake of simplicity, we're just using like a y gate that has like its exponent, right? So if the exponent is the same, then it's obviously going to be the same state, right? If the exponent is different, or even let's say that, for example, what if I add like, so these, right? So this is different in the sense that like a Bloch sphere here will show you that this is sort of halfway here, and so it's not zero anymore, right? Um, the probability, they're nevertheless really similar, right? The probability of measuring zero is the opposite of these. So it's like, you know, uh, it's more than 93%. So they are quite similar from that perspective. If I take this one, right, you get they are orthogonal in the sense that I know they are not orthogonal in the Bloch sphere, but they are orthogonal in the sense that they are completely opposite. The Bloch sphere is falling here, but then you get this 50%, and kind of you have all the range in between. So if I leave it at the state 0, you're going to have a 25% chances, so like 75% chance of being 0. So what this tells you is like it's kind of halfway of being the same between their orthogonality and right, but it doesn't really matter. You understand the point, right? So if you this is my intuition. My intuition tells me that if and if you take a look at the way that Brian does this, it's actually, I mean, he's pre-computing the parameters for the U3 gates, okay? And even if you go simpler and say, because what he's doing, right, and this is actually an awkward thing to do, and I don't think that's a correct thing to do, to be honest. I'm not so sure. It's not so obvious to me that if you, because I'm telling you, I think he's encoding two. So what he's doing is he's encoding uh, like two of these values as two of the three parameters of the U3 gate. So he's, I think, using these two parameters because the lambda is basically a z rotation which you can ignore if you start with a zero state. So I think he's encoding these two parameters in here, right, and then calculating the overlap of these. But that might be correct. I mean, in the sense that, as I said, like if you have the same set of angles, like if I have two U3 gates, right? I mean, let's do this, okay? So let's start with a small example. What I want to do is I want to try to understand. So here we have the let's even simplify this more because it's going to be easier to visualize. Let's imagine that we just use like an RY rotation or an RX. Let's use an RX, I don't know, or RY. We can just whatever, RY, because I think he's mentioned this before. If you have an RY rotation, this RY rotation has one parameter, which is the angle, right? So what you would do is you would kind of encode each of these elements like times pi probably, right? So you would say, because this is a normalized value, is between 0 and 1, so you would say that proportion of pi. And so you would, this would be 0 times pi, this would be 0.001 times pi, and so on and so forth. And so you would encode these. How can I approach these? So how can I approach this in a more systematic way? Like you are encoding these in RY rotations, and then what I want to know is what's the where's the Wikipedia. So let's assume even the simplest case where this is just one qubit and this is just another qubit, right? And let's do this. So what we have to calculate is we have to calculate these I want to express this function with SymPy, right? So you have so how to do this. How to do this with SymPy. So what we want to have is oh, by the way, if you do these, like if you run this code where it just calculates your Euclidean distance, like it classifies my, like, also, like, I mean, pretty well. I don't know. It's just that's the shortest distance is to the 0 element. It's similar to the 2 and the 3, 0.29, 0.28, but that's the shortest distance. So it classifies this correctly, and it does this like in a just matter of seconds or milliseconds. So not like 4 minutes, which is I think what Brian's circuit takes. But I get it, like this is an Euclidean distance, so it might not be quality-wise the same. But what I'm trying to prove here is I'm trying to prove that if we have this specific set of sorry, it's messy. If you have this concrete construction where you have single qubit rotations, and all you're doing is parametrizing them with these values, like you can just compare these values, and that should tell you the same. The closer they are, the more probable that element belongs to that class, right? Intuitively seems to make sense, and thinking if there would be there would be like a formal way to prove these though. But okay, let's see. What do I want to do? I wanted to do a small example and plot this. So I wanted to take a look at this. So this is the function that we're trying to have. So it's 1/2. I'm going to be losing these quite often, so I'll just organize the tabs here. And I need SymPy. I'll need to check that. So I open, because I know you can plot with SymPy, but I'm like, okay, so basically we have an expression. So this is the probability of measuring 0. It's basically 1/2 plus 1/2 times, and now you kind of have, okay, so SymPy absolute value complex absolute value, just absolute value. Arc, no apps. If you define your symbol list with the attribute real true, then you will get the correct expression for it. With your SymPy symbols given as complex, and apps does not know the real and imaginary parts of these pieces. Instead, so the output of apps cannot give you what you expect. That's going to be tricky to do. How do I expand complex true? How can I do this? So because this is a transpose of, maybe I don't even need to use the complex numbers here if I just stick with the, what is the RY matrix? Quantum RY matrix. Because the U3 gate has got some complex exponents and stuff like that, so this is gonna be funky too. But I can try to do it by hand, maybe. I want the R. That's not what I wanted. That's not what I wanted. RY gate, the Qiskit documentation. Oh, there's actually, of course, yeah, there has to be a complex component. Oh no, actually it's just like that, like in use the matrix like that. Okay. So I basically need the this is where so I have the what I want to do is I have the so I'm starting with the zero state, and then I'm applying like a rotation on like whatever angle here, right? So this is for one qubit, that would be like these times and then the RY matrix. So I want to get that into SymPy. SymPy. Right. I just used it for the portfolio stuff, and I already forgot like SymPy matrices. So what I want to do is I want to have the so how do I find a matrix like that? Okay, so and how do SymPy cosine? How do I define those things? Just like that. SP cos, and then the symbol, right? So here we have just one symbol, which is one angle, but we have two symbols because we have two angles, because we have two qubits. So actually we should do like I'll just call it X, and Y is like SP symbol. X and Y is SP symbol. Y, and so what we're now doing is SP matrix. So we're doing now these, right? Cosine minus sine, plus sine, cosine. So we're doing like a SP cosine of x divided by 2 minus 1 times sine of x divided by 2, right? And then we're just getting the same down here, but it's just sine and cosine, I think, right? So this is the matrix. Oh, that is probably this is the norm squared, not like the this is the norm squared. So what I want to do now is I want to multiply these by another matrix, which is basically 1, 0. So that's the ket 0, right? And I want to have everything transposed, actually. Because, can I not define this in a more modular way? Is this going to complain or not? Does complain. Symbol is not defined. Tuples. List indices must be integers, not slices. Let's maybe get rid of these for a second. Ah, tuples, okay. Or what is this? Oh no, like, oh wait a second. No, that's correctly defined. That's correctly defined. Oops. What did I just... Still complaining. List indices. Oh. How do I print things nicely? I also forgot. Print nicely. Pretty output. Was init printing? Was it like this? SP init printing? And then I say print. That's not nicely printing anything. Oh, I think this was only working as long as I just was doing like these. I think that prints it nicely. Yeah, that prints it nicely. Okay, there we go. So we have this matrix. So this is basically the AY matrix expression. Cool. The transpose SymPy. What I'm trying to do, what I'm really here trying to do is I'm trying to basically make the function and plot the function, so we can see that as those kind of variables get close together, there's where we have like that maximum or minimum. I don't know what we're gonna see. Yeah, that's the transpose, right? Yeah, that's the other one. Cool. So the transpose will be like these. Okay, perfect. Now what we need is we need kind of these times. Okay, these times like SP matrix. 1, 0. So what you have is just like these, right? Because you just have the 0. This is the ket. This is like the ket 0. So basically, you know, this would be something like the AirY of x times the ket 0. Kind of. That's what we're trying to do here. Because that is basically, it equals our, like, let's call it state A, right? Or like Q, yeah, this is cool. What we're now going to do is B is basically the same, but with Y. So this is another parameter, right? Cool. So this is basically Y. This is basically Y. Cool. So this is basically ket A, and this is ket B. We want to compare ket A and ket B. Ket B is it's on Y, and X and Y are the two angles, right? In this case, the two data points. And cool, so we have these. So now we have these we can build these, but now how do I say the norm? So SymPy matrix norm, or it's the vector norm. Norm. Why is it so slow? What's going on? I'm gonna close this. SymPy matrix norm. Norm with norm. Okay, that's norm. Normality with norm. No, that's their normality. Oh yeah, what's their norm exactly? That's correct. So what we now want to do is we want to have here's where I am. So really, what the express can I do like can I do these like ket A plus ket B and then print A? Oh yeah, okay, that's nice. That's neat. Cool. So what I can do is now I can basically say, well, I have like my prop 0 is basically 1.5 plus 1.5 times, and now I say, well, ket A transform times ket B, and from these we want the norm, and we want it squared. And now I want to know if this is gonna work. I'll be surprised. What do we have in here? Oh, nice. Okay, so we do have, yeah, so we do have something here. We do have something here. Now, cool. Let's test these. Okay, so if I like, how is the replacing thing? So how is the SymPy replace symbol? Substitute. Subs. Okay, I can do something like that. I can just do something like these. Okay. So what if I say, sorry, I'll just call this prop 0. That's all fine. And now what if I just say prop 0, substitute x for like, does this have to be like in like radians? I think so. I think this is going to be in radians. How do I know that though? Attributes, label params, RY gate, theta. Doesn't tell me, that's bad documentation, but I'm going to assume it's pi. Don't kill me for this approximation. So we're going to give it the same value, and it gives me 1. So this means the probability of measuring 0 is 1. It means these two vectors are the same. If I replace these with like say 1 is 0 and the 1 rotates, then we have 0.5. Nice. Okay, so it seems like this is working. Let's see if we can plot these. Okay, let's see if we can plot these. Whoa, plot. I lost it. No, plotting here. Okay, so how do I plot these? I have this thing. Okay, so there's this plot function, and then okay, so I can just say plot and give it the function, right? That's it. That's pretty cool. So I can just say plot prop 0. Well, I obviously have to do it like this. Oh, univariate expression is being plotted. Phrase symbol. What does this mean? Should I give it like? Should I give it? So SymPy plot to 3D, right? I think this might be different because it's probably a 3-dimensional plot. How do I do a 3D? So you can specify the ranges. Well, plot 3D. Okay, so there's actual plot 3D. That's neat. Would it just work out if I just do these? No. You gotta have plot 3D. Plot 3D. It's plot 3D. Plot 3D. Come on. You have it. Don't tell me you don't. Plot 3D. Why do you tell me you don't have it? Module SymPy has no attribute. Plot 3D. Should I import it like this? Should I just... Oh, that actually opens... Oh, that's cool. Just wanted to import these. I should close some tabs. Okay, it's plotting. Yeah, but I want to see. I want to see the plot. It would be nice if I could see the plot. You know. How do I plot the whole thing? Plot 3D. So plot 3D SymPy doesn't show, doesn't appear. Is it like a parameter that says show true or something like that? Will not display the plot. Will not. So by default, session false in the function will not display the plot. Also, it has actually something called show. So if I probably has it as well. So this is I'm gonna show it, or oh yeah, oh cool. Oh nice. Okay, so how do we interpret that? Yeah, well, basically, so what are the variables? So it's kind of like a wave, right? Yeah, basically, but okay, so what if I give it like, can I give it the range between 0 and pi? That's what I want to give it the range. So what was the ranging thing? Expression 1, range 1. So plot 3D arcs, expression, range x and range y. So arguments. Okay, so something like these, right? So if so now I can say x is between 0 and 3.15, and this is between this is y is between 0 and 3.15. Okay, cool. Can I rotate this so we can see what I mean? Like to rotate that or orient that somehow. I see that I don't need to show it, now it appears for some reason. But you can kind of see that the diagonal, right? It's where you have the 1, is where it's the diagonal, right? So it's kind of where both x and y are the same. So everything else kind of fades away, right? And I think I lack the skills right now to see if I could formally prove that for any number of dimensions. So it kind of feels like at that point, right? If I just compare if I just compare those angles, right? That should just be it, right? I can't thing is I can't play with visually with more variables because I'm not going to be able to display like a 4 or 5 or 6 dimensional plot. But that should give you an idea of where my intuition is going, right? So if you know the parameters, if you know the parameters that construct your state following that specific recipe, you can just compare the parameters, and that's it. You don't need to do these. Like, you don't need to do this thing. Now the question is here, like, what is then, because I can do this because I can do this formula because it's one, it's comparing 2 qubits, right? Obviously, if I be comparing more qubits, then kind of like that's the way that I've done this here, kind of doesn't make sense. Like, you wouldn't be able to do this because you just basically would not be able to, at some point, compute the sizes, like, or hold the sizes of the matrix, right? Like for like 100 qubits, then you'd kind of have like those matrices would be pretty big. But I think actually with a tensor network you could do that. Maybe would they be that big? Because these here would still be like a 100 elements column vector. And these matrix, to be honest, it would just be like a huge identity. So you don't really. It's like a huge identity, and then that little matrix, and the place where the specific qubit goes. Yeah. At this point, I'm thinking, what else could I do to prove these, right? so what have I done here? So what I've done is I just run a basic Euclidean distance and sorry, yeah, exactly here above, yeah. And so, what would be something that would be convincing enough for Brian to understand this? So if you compare, my point is if you just calculate the distance between these test element, right, and any of these, like, and that's what I meant by like I can do it in the calculator, right? Like I can actually, like, if your computation takes 4 minutes, I can actually in 4 minutes really kind of calculate this distance. I don't know if I would it be doable? I don't think actually. Maybe it would be too cumbersome to have. I don't have enough variables in the calculator, so I'd have to do this by hand. But I can calculate 10 distances. Would I be able to do this on the calculator? I'll try, okay? But that's gonna be the next video, I think. I'm gonna have to have a smart way to do this. But I don't know how else to show this to you, Brian. Um, or how else to kind of thinking if there would be like a formal way to prove these. There'd be a formal way to prove these. Probably, mathematically speaking, you could. Um, you could try and say, well, I have my. Like it's got to be. This is the shape of the function. It's got to be. It's got to. I mean, how can it generalize these? How can it generalize these for more dimensions in a way that Brian can maybe understand the proof? Or that I can actually see whether the proof really scales to more dimensions. That could be definitely an interesting exercise. So what am I trying to prove? What I'm trying to prove is I'm trying to prove that if you encode like, and here you kind of have so here would be different, right? So what Brian is doing is encoding like a pair of things. So if I want to be fair with him, I would actually have to say, I'll take half the qubits. Like it's a bit more complicated because you kind of have two dimensions. So what I would have to do is that I would have to split these in two, right? So this is 16. So I have to have like 2, 8, and then split those in two as well, and kind of calculate the two distances, and this would be where kind of the average distance is the smallest. That will be the equivalent of the U3 gate. I mean equivalent, not equivalent, but like something you could do. So the closer the points, if I'm, but I think if I'm able to prove that regardless of the amount of variables, you're always going to have a maximum where the two variables are equal, right? And everything else is going to be smaller than these, then I think that's a good enough proof that like calculating then just running the distance between the points, it's what you want to do, because you kind of have, okay, so how far away are from each other if you think of those points, of those vectors being points in one in you know, whatever n dimensions. Mm. So the thing here is you have these, right? So what if ket A and ket B like would actually have, like, let's say a third, like let's say these are let's say, let's imagine that this is a rotation on y 0, and then we want to have a rotation, because essentially you would do it this way, right, on y1. So that would be like on, say, p, right? And so here you would have ry0. So what I'm doing now is I'm basically, it's going to be q. So I'm adding two more symbols. Okay. Maybe you know what? I should just do this. I should just do this properly, and I should just do it in another cell. So this is P and this is Q. This is P and this is Q, and so that's what we have. And so what we have now is now this matrix is only gonna apply to qubit 0, because now the matrix needs to grow. So this is basically 0. This is basically 0, right? So these kind of grows like that. And what we have here now is that we want, let's see how would this look like. I would have to multiply, because this essentially means, not these, I'm looking at these here. So this essentially means, what this is, these two elements are the one component at the top, the second component. I think it's just like an identity, like you just have to add, it's just the first quadrant. I think that's what you're doing, if I'm not wrong. So what you have is you have like something like a so the first two rows will just be, the first two rows will just basically be, you know, no, so it's going to be four, it's going to be four rows, okay? So it's going to have 4 rows and 4 columns. And so the first are going to be 1, 0, 0, 0. This is going to be 0, 0, 1, 0, 0, right? And then here you're going to have 0, 0, and then these two. And I think here have 0, 0, and then these two. I think that's what you're going to have, if I'm not wrong. And so here you should have the same, basically. Or what's more, just copy the same, but replace So this is kid A, and now replace these by X. But now you're going to have a more complex, so you're going to have another multiplication. So what does this give me? Okay, B, I wanted to just see these things. Yeah, that's the shape that I want this to have. But now you're going to have another another product in here, which is basically going to be the same, right? But just on not the same, so similar. So you're going to have these, and you're going to have, I think that's the way you would construct it. I'm sorry if I'm wrong and adding a bit of dyslexia in here. So here and now you would have like a 0, 0, 1, 0 and like a 0, 0, 0, 0, 1. So I think that's what you would basically have. Yeah. And if I copy these, here, but now this is basically P. And this is basically Q. There's people faster than me typing these. That's basically what you have. I think that's what you have. And so, you know, but I'm not going to be able to plot these, obviously, but at the end you have this could be like that. And so if you now take these, something's off in here, I think. Kid A transpose. Why is it only dependent on P and Q? I think I might have, I don't know if it's right, to be honest. I think I might have these the other way around. I think that is kind of like these, but like, doesn't matter. Why am I getting, they should be a function of x and y as well. Or is it that they cancel somehow? But they shouldn't. Why would they? Like if I don't, if we don't multiply them by these, what do we get? So if I comment these, what do we get? What are the x's? They just disappear? I think I'm doing something. I think I must be doing something wrong. I think I must be doing something wrong. So, how can I figure this out? Come on, this is basic. This should be pretty basic. I think I'm multiplying, I'm just doing the wrong thing. Like if I take those things apart, I should have done this better. Better like that. So if I just take these and I call these rotation on y1, and now I say, well, sorry, y0. Rotation y0 equals these. Now I take this part here, y1, position y1 equals these, and I'm going to comment on these for the moment. And if I print y0, what am I going to get? If I print arrow y1, I'm going to get these. Is this the right thing? Times ri0, then again like this, times so okay, so ket0 is basically this for everything. So times ket0 times ket0. Can you start expression here? Why not? Oh, sorry. Oh yeah, actually that kind of makes sense. Wait a second. So it's only affecting the qubits. It's only affecting 2 of the qubits because, right? Makes sense. Yeah, that actually makes sense. Because here we're just applying these to the ket0 and we're just applying like no. We should see so we should see the ones with the x in here somewhere. So ry1 e cosine of p well actually there should be a way to programmatically do these, not just by hand, right? I need more coffee. I'll go for coffee. Sorry, actually forgot to restart. I was here. Yeah, so basically, coffee. So actually, if I just googled that, I just googled how to input 2 qubits into Hadamard gates, and actually it's just the tensor product of the same gate. Like, so you're doing the tensor product, the matrix product, right? no, the tensor product. So in SymPy, tensor product is that's what we want of the two gates. So simply tensor product, and then you get these. Is this the right thing to do? I think so. I think that's what you do, because this is first qubit, this is second qubit, right? I assume. So it's the tensor product. Okay, yeah. Maybe not, because that's with a Hadamard layer. Oh yeah, okay, no, but what's saying is you can just distribute these things like that. I'm not so sure that's a general way to do these. Would you just do the tensor product and that would be it? So here, say if you apply the Hadamard on this qubit and this qubit, no, you can't generalize that, I think. How to turn one qubit gate to another? No. What I wanna do is matrix applied to a given qubit. I just want to have the matrix of applying multi-qubit quantum gate to specific qubits. That's what I wanted to do. Expand the operations. ISO back. Controls are easier. Yeah, controls are easier, exactly. So that's not that simple. Number of qubits being simulated. Logic gate matrix of size 2 by n, 2 by n. Oh yeah, that gets spread out like these. It gets spread out like these. Define the operation of a qubit must be on control to be okay. That's controls are easier. Gate or subset of qubits. No, but that's even more generic. I want to so I want to apply, for example, these gate to only, so this matrix, right, to only like qubit 0, for example, right? So how would I do this? Thinking about this maybe with paint. So if I have my, like, it's a 2-qubit system, right? And so I have like the A, B, C, D thing, and this just applies to kind of like one qubit, right? Like x, y, and I won. But now the system that I have is the tensor product of x, y, and x, y, right? So you kind of have like all these like x, 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 y, y, x, y, y. And I want to apply that's so basic. That's so basic. And I'm stuck at these. So I thought that would just be as easy as these, but it's not. It's, I think, somewhat spread, but how could I build it? So you have, so I have the air y, like I have the air y matrix, right? Which is basically like what I have here. That's the air y matrix. Yeah, I'm running out of time, to be honest. That's the air y matrix. And I want to apply this to the just to the second qubit, right? So what I want is what I would like to have is that if I apply, so if I apply, you know, I have these bigger metrics, which is going to be like 4 by 4, and I want to supply only to the second qubit. So this means what does this mean? I mean, that's so basic. That's just so basic. It's just basic math. It should be basically in your algebra. Apply a Hadamard to what? Specific qubit. With 2 qubits, multiple qubits. Oh, here we go. So this is okay. So this is the Hadamard and the X. So what do they? Okay, so it is indeed the tensor product. What you're doing? Okay, it's the tensor product. Okay, cool. I need to understand this a bit more. But this means that what I'm going to do is I'm going to do, so the air y on x and the air y on p, I'm going to basically kind of, meaning the parameter x, the parameter p, so this is going to be like these, and this is going to be like that, and this is going to be like that. And now what I just say is that what I want is I want the tensor product of those. So I want the tensor product of those. It's basically SP tensor product. So the RY layer that I want is the tensor product of RI. Let's say P applies to the qubit 0. So I think this means that I need to put in here RYX and RYP. Now I have this R layer, and then if I do, what does this look like? If I print this, tensor product, SymPy tensor product. Thanks Qiskit for the help out there. SymPy tensor product. Oh, I gotta import it this way. So then I will just call tensor product. Okay, so this is the matrix beast. And now what I want, so I wanna, well, I kind of feel like, to be honest, I can just already do like Y and Q, and so this is kind of, you know, Y and Q. This is Y and Q. This is Y and Q, and this is Y and Q. And so the rotation layer, no, and now what I do is I just do just like this. So ket B is just the tensor product it's just tensor product of air y y and air y q, and the ket A is going to be x and p. Exactly. Cool. Y2 is not defined. Where have I made a mistake? Where have I made a mistake? In here. In here. So this is what you have. Okay, so it depends on QP and KA. Okay, that's right. Cool. And so now if I do this, what do I get? So I get this beast. Cool. As you can see, this grows. 1, 2, 3, 4, 5, 6, 10, 11, 12, 13, 14, 15 or so, 16 or so. So it's like 16 and we've got like 4 parameters, right? Yeah, it's basically 2 to the power of 4, right? Oh no, that's what did I just say? Yeah, 16. So it grows exponentially. So this will grow exponentially. So it basically okay, it grows exponentially, but we can see already a pattern. Look at these. So it's always So it's always a multiplication of sinuses and sinuses and cosinuses, right? What you have in here. And now if you remember well, like what's the like when P and Q and X and Y, this is all sinuses. When it's then sinus times cosinus cosinus. So it's got 4 components. But what this tells you is that if they're all the same, then you're gonna have like sinus squared plus sinus squared. No, sinus squared plus. Yeah. I think that shape is what's gonna. That shape is what's gonna basically. What's important. I think as we grow the parameters, this becomes intractable. But I think this is gonna tell you that this basically this pattern that is like you're getting this product of the sinuses and the cosinus functions, where I think that really indicates that the shape of this function is going to be like that, where all the parameters are equal. Then this actually sums. This is really what you kind of want to have. Like this really sums up to the right value. I'm gonna get these. I'm gonna prove this. Okay, I'm gonna stop here because it's really late. But I'm gonna do I'm gonna try to do a formal. Go ahead and do a formal proof. Yeah, I'm really gonna do a formal proof. I like to do a formal proof in these, and then basically show that with these rotations, like this is the shape that it's gonna take, and then we can also do this with a U3. So I'm gonna save these, and yeah, I think that's about right. I like it. But it's obvious for a simple case, right? So that only when the parameters are equal is when you're going to have like the equal thing. So I really want to actually do the formal proof here. But yeah, it basically classifies the stuff. It basically classifies the whole thing just quickly, just with an Euclidean distance, right? Which is, you know, how close they are from each other, these points. And I see that this is really growing this way, so I'm gonna. So basically, it's the sinus and the product of all of them, and then the sinus and the cosinus and the product of all of them, and then the sinus of xy and cosinus pq and sinus pq and cosinus xy. Yeah, exactly. So that really already tells you that it depends on these. But let's try to do a formal proof, okay? I've never done a formal proof. Cool.